Good morning. Welcome back. So in this chapter, chapter number one for our textbook for COSP7 class, I'll be discussing this chapter and I'll go over the material in the chapter number one. Now, some of the material in this chapter, which you can see it's called Introduction to Computers and Programming, is going to be pretty self-explanatory, and you will find a lot of things you already know, especially when it comes to basic definition of hardware and what exactly it entails. Some of the information, maybe in the middle of the chapter, you will see some additional new information you'll find. The main focus is we understand what the software is because this is not a hardware class, but we need to understand some of the basic components of hardware as well. So let's go and get started. This will be a brief discussion on this chapter. I would say maybe 30 to 45 minutes. And that's what I'll do. I'll try to make the recorded lectures much brief. In that way, you can focus mostly the time on reading the material in the textbook, completing assignments, and doing other productive things. So the main focus is not the presentation itself. The main focus is that highlighting some of the key components which are going to be part of your exams, part of your assignments. So in that way, you can focus on those new areas. So in the second slide, let me take a look at this one. And I think you can see my view here. Um, I just want to double check. Okay. So in this chapter, the first thing that we will talk about, this is the objective screen. Basically, computers are being used. Now, this is just limited scope here, but they're used in every aspect of our lives these days. In fact, you carry your computers in your pockets. You go to work, you go to school, you are entertaining yourself. You are basically using computers for all purposes. But in this particular slide, it says they're used for research and writing papers, emails, online classes, just like this particular class as well. You can also use at work for analyzing data, and especially these days, we are talking about artificial intelligence. That's where we are using a lot of computers and how the data is analyzed, and we'll talk about more about it a little bit later. Also for making presentations, just like what I'm doing right now. Transactions, all sorts of transactions, banks, credit cards, when you go to a retail store, online purchases such as Amazon, and a bunch of other things. And of course, social media, such as communication on social media. Now, the mode of communication have changed in last several years. Instead of typing or speech, there's a lot of images and video games and those kind of things have emerged in last maybe 10, 15 years. So the way we communicate has modified significantly. And any of the control machines, especially in factories and banks and other machines, which we are not directly as consumers using those machines, but behind the scene, the industries and factories and many other organizations, they use those machines as well. And of course, we are paying our bills, we are shopping online. I have already indicated the video games. In fact, I hardly get an email. All the mail comes through my email or directly to my particular bank. All the bills come through those. So that's how we are paying our bills, credit card bills, and that's how we are interacting with the other organizations as well. In the following slide, so now you might laugh at this slide here because it says MP3 player. I'm not sure too many of you are using MP3 players anymore, but you can see that the emergence of newer technologies have really taken over, and we are using various types of devices such as smartphones. Smartphones are way powerful, very powerful computers, and of course, you probably use an iPad or other tablets. And GPS, we don't have the GPS systems separate devices. But 15 years ago, they used to be separate devices you had to purchase. If you you don't even know, your parents probably know there was There was an organization called TomTom, Magellan. Many of these organizations don't even exist anymore because now the GPS systems are basically built into your smartphones as well. And there are many other devices use on daily basis. So why do we use computers? So computers are designed to do any job that are basically they can allow you to write programs and to do something with the programs. Now, that's the focus of this class as well. And I also will be spending a lot of time discussing what the program is. So the basic definition of the program is set of instructions. So you give instructions, and the instructions must follow certain syntax. Syntax means grammatical rules, just like you're writing an English paper. You follow certain rules. Where do you put a semicolon or a comma? Where do you put a space? How do you put how do you follow the grammatical rules in order to make proper statements or sentences? In computer programming as well, when you're writing a computer program, you follow certain instructions by following certain syntax as well. And normally the program is designed to do a specific task. So let's say you want to add numbers. Let's say you want to move an object from place one to place two. So the computer program is designed for that purpose. Of course, we are not talking about primitive programs. Now the programs have become very advanced. So the programs can do a variety of things seamlessly, simultaneously. Some of the programs we use, browsers, Microsoft Word, PDF files, PowerPoint, like this particular one here, video games, and of course, everything that you see on your smartphone, all these are computer programs. And we also call computer programs as software, and that's the key word we use. But if you hear some other names, which we'll be highlighting in this and future chapters as well, such as code, such as instructions. So you might hear some other keywords as well. They all indicate they're referring to computer programs. So you might hear software designer, software developer, software engineering. That's what it indicates, somebody or a mechanism where you can write computer programs. All right, so programmers or computer software developers, as I indicated in the previous slide, are the individuals, either one person or a team of people. They create computer software. If the software or the program is much simpler, primitive, not very difficult, probably one individual can develop it easily. But if the software is very large, we are writing a code for a large organization, an airline, a bank, such as Amazon, then of course you need many developers working together. They work on different aspects of the system because you have a back end, you have a front end, you have the middle tier, you have the database connectivity, all sorts of things. You are analyzing the data, you're projecting the data. So in larger systems, many different developers or software developers, they work together to create a larger system. And of course, when you're learning something new, especially you're learning a language and a different language, then you probably need some kind of a skill set. And that skill set, how to design it, how to create it, how to test it. So there are different areas people specialize. Some people might specialize only on the web development. Some people might specialize on the CRM system, customer relationship management systems. Some even develop either they become expert in ERP systems, enterprise resource planning systems. Some even become expert in cybersecurity. So you can see there are many areas or even app development these days, for example, for your smartphone. So people they develop a skill set, and for each skill set, they might have to learn different skills. They might have to learn different programming languages. So that's what we are going to investigate further later on. But that's what the goal of the developer is. Many of these developers, they start something intro to programming. Many of you probably will take my class or somebody else's class at Long Beach City College or maybe other places. And that's how you are introduced how to write your first piece of code. And then you might be interested and you might develop more interest in that one. So you might take an advanced course, a data structure course, an architect course, It is possible that you can actually get an associate degree in computer science in our department and then transfer to a university in that particular area in computer science. Or you might move on to other areas such as information systems, computer information system or management information systems. But if you look at a bigger schema, all organizations, all business or non-business organizations, they use computer programs behind the scene. Everything you touch these days, they have some kind of embedded code behind the scene. The cars you're driving, the devices you're using, the workplace, doesn't matter you are at Taco Bell or you are in McDonald's or you are at airline or you're at the airport. Everything has some kind of computer system embedded, and somebody probably has worked on it, or somebody's maintaining it. So this is the extensive usage of the computer programs these days. Now, some of the concepts, like I stated earlier in the beginning of the chapter, that might look pretty simple, and it is very simple. And those next few slides will be pretty straightforward. So I will not be spending too much time on those, especially when it comes to hardware. But then I'll be focusing mostly on the software side later on and in the future chapters as well. So the concept, the physical device is a tangible device, something you can touch, such as a computer is made of many different types of hardware or components. The programs run on a computer that refer to as software. So you have a physical device which is tangible, and you have something intangible, non-tangible, something which you cannot touch. So imagine if you have a physical body which has limbs, which has physical components, and inside you have thoughts and ideas. So the program is like your thought or idea, and the physical body is your hardware. So you have hardware and software working together. That is called information system. And of course, it has additional components such as data and other things, which we'll talk about it later. But right now, there are two key components here. One is the hardware, the physical device or collection of physical devices, and the other one is the software. All right. So the hardware is physical devices that a computer is made of, are we call them hardware, and computer is a system devices that work together. So pretty simple and straightforward. So some of the things you might hear in this chapter as well as in the future and probably in the marketplace, it consists of various types of components. So one of them is a CPU. Now, in other textbooks, other authors, they will call CPU as a brain. This particular text and the author doesn't call a brain. And I'll actually allude to that one, why this particular author is not calling it a brain. But CPU is the most important component of a hardware. That's where most of the management, most of the processing takes place. But other than CPU, there's the main memory, which is called RAM. That we just call it memory. Then you have secondary storage. Secondary storage is your hard drive or your USB or other type of storage medium. It could be cloud storage as well. Then you have, just like our limbs, we have our hands and our arms and our legs. You have input devices. So input devices allow you to take the input data. And then you have output devices such as your printers and monitors. Those are basically to project the results. So because when we take the input data, we have to process the data, and data is being processed by the CPU with the help of CPU in the main memory. And some of the data probably needs to be stored in a secondary storage in the hardware. Some of the data probably needs to be processed in the main memory. And then after the data has been processed, we have to project the results. That actually happens in the output devices. So typically you will see these components here. And the CPU is one of the most important component, the most expensive component. It allows you to run the program in the CPU, and CPU has many additional helpers, arithmetic logic unit and memory and other things. But typically, whenever we talk about CPU, we simply say processor. So that's basically is like I stated earlier, it's like a manager, like a brain. Again, but this author actually doesn't like to call it a brain, but it is actually kind of brain because that's where you are running all of your ideas and producing and being creative and producing some results. So that's what the CPU does. And this author says that without a CPU, a computer cannot run the software, which is, I agree with that one. So running or executing a program is the term used when the computer performs a task the program tells it to do. So when you hear a term, I'm running a program or I'm executing, that's what it means. Basically, the CPU is actually processing whatever the input instructions are and producing results based on that one. In the past, in the beginning of the 20th century, some kind of primitive devices were developed, and gradually, ENIAC was considered as the first programmable computer. And these were very large machines. And believe me or not, many of these machines were managed and run by women. And many of the men at that time, they were busy in the Second World War, but a lot of these devices, a lot of initial developers and programmers were women at that time. And so the ENIAC device was built in 1945. It was designed to calculate artillery ballistic tables for the US Army, as you can see, because that was the need of the time. And that's what they were using. And also, they were using for census, they were using for research. Many of the universities and hospitals were involved in the development of early computers. These computers, ordinary people did not have the access, did not have the understanding how these computers will work. So these were very specialized devices, as you can see, that these are 100 feet long, 8 feet tall, and their weight was about 30 tons. Mostly they used vacuum tubes or similar kind of components in the back. So these were very heavy. They needed a lot of energy as well as cooling systems. Then gradually, um, in 1960s and early part of 70s, we basically moved on to something called processors, and the processor was smaller, much more powerful. Of course, we have skipped in 30, 35 years of the development processes, various types of components are developed. So we are not going to focus in this class what other devices were involved, but you can see this image that process is being highlighted. And the processor is basically your chip or your main brain, which does all the processing, and it's the most important component in any computer machine. The main memory is called RAM, random access memory, considered as the work area. And that's where computer stores the program and runs the data and processes the data. And the full name is random access memory, but sometimes we simply call it main memory or just memory. Data can be easily accessed from the main memory. And the RAM or random access memory or memory is volatile in nature. Volatile, it means it needs the source of power all the time. So if the source of power is not there, RAM is basically not very useful. RAM is, I'm just checking here something. Uh, yeah. So RAM is basically a volatile in nature, used for temporary storage because it needs the source of energy. So if there's no source of energy, then of course you would lose all the content. So that's why it's temporary in nature. RAM is erased when the computer is turned off because there's no source of energy at that time. There are other types of memory as well, such as ROM, and many of you probably have not used a CD. In fact, we used to call it CD-ROM, compact disc read-only memory. That was the full name, and but 15, 20 years ago, a lot of people were using for storage purposes, for music, for videos, for DVDs. All these were different types of ROMs. A computer can read the contents of ROM, and ROM is also a chip in there, which has the data which is stored kind of permanently. It is non-volatile in nature. It doesn't lose the contents if the source of power is not there. So that is actually some kind of initial instructions are stored in the ROM. So how to turn on the machine, how to load an operating system in the RAM, all other instructions, especially BIOS instruction, basic input output instructions are stored in a chip like a ROM. And they're important for the system operation, like I indicated a couple of things. So the ROM is also an important component they're built into your device. Then I indicated the second storage, which holds the data for long periods of time. We need the data to be stored, such as videos, pictures, data, spreadsheets, documents for years and years, for thousands of years. I'm exaggerating, for hundreds of years, for example. Imagine if there's some kind of research you have to do. The bank actually has to go back to the data from 1960s or 50s. So where do they store the data? Because the random access memory is only temporary in nature. So they store in a permanent storage medium. And the hard drive is one of them. We are very familiar. We are also familiar with thumb drives or USB. These days, we're not even using them, but these days, mostly we use the cloud storage. We'll see a slide on that one, I think, in the next one. But disk drive is common type of storage. Data stored magnetically, and the typically hard drive. And many of these modern computers, they don't even have hard drives. They have something called that solid state, which there's another slide which will highlight that one. But still, if you have a device which has the hard drive, it actually has some kind of platter, and there's a head on the platter which moves very fast. The circulation often you can hear the noise of the circulation. Zzz, that's where the data is stored, and the data can be stored for long periods of time. Now, of course, it is recommended to make backup copies of your data just in case if something goes bad, and then you have this storage. Now, the solid state drivers or devices are very popular these days. They're a little bit more expensive, but they don't have any moving parts. So, and they are like a big, just like your thumb drives, they're big thumb drives, and they're smaller and more compact in size. And because there are no moving parts, so the tendency of losing the data or going bad or touching something physically is not there. So it actually much more faster and a more durable. So if you're purchasing a brand new laptop, for example, this year, I recommend that you go with a solid state drive. These days, you can easily find a laptop with 1 terabyte solid state drive. It will be a little bit more in price, but it will be much efficient for long term as well. USB drives, I'm not sure how many of you still carry them. We used to carry the diskettes, CDs in the past, just 10, 12 years ago. Then before that, we used to carry even floppy diskettes. When I started teaching at Long Beach City College, in fact, that's how the students were submitting their homeworks. They were submitting their floppy diskettes. And believe me or not, and then I started collecting CDs as the homework and you would argue that what about the Moodle and the Canvas or Blackboard? None of these platforms were available at that time. We did not have Canvas. Before Canvas, we had Moodle, and before that, we had Blackboard. None of these platforms we had access to them. So this is how we collected the homework. This is how I collected the homework. Then later on, USB, I would say last 4 or 5 years, it has not that popular, but this is how we actually started collecting homework as well. It does not contain a disk. Data is stored in a flash memory, also known as a memory stick. Flash. It's pretty inexpensive. Many places you go to conference, you can get a free USB drive, and it's pretty handy. I still use it personally because a lot of the attendance and a lot of other things which I want to carry quickly, and you can easily plug into your computer and just start accessing the data. I indicated this one earlier. CDs and DVDs, you don't see very frequently these days, but data is encoded as a series of pits on the disk surface. Users uses a laser to encode the data, holds a large amount of data. And it's a good way to create backups. Not many of you are using these anymore. This is what a lot of people are using. In fact, all the social media data, your Google Drive, and all these things are happening behind the scene. They're using cloud storage. So data is stored in the cloud, storing or removing server via the internet or via a company's private network. You can access it from any device. You can access from your smartphone, from your computer, from iPad, and you basically log in and you have access to the servers in the backend. These servers belong to large organizations such as Amazon's AWS or Microsoft's network. All these are basically quickly access the data from anywhere in the world. You don't have to physically carry anything. And that's how organizations are also using the cloud storage. Again, we are familiar with some of these input devices. So these are basically Data collects from the people, and the hardware devices, they allow you to collect the data for input purposes. It's called input devices such as keyboard, mouse, touchscreen, scanners, digital camera, microphone. These are all input devices, very self-explanatory. So output devices are basically you project the data, which I indicated earlier as well. And you actually have some kind of output device such as monitors and printers and many other types of output devices as well. So this is where our main focus would be. So software is basically your program, and every computer must be controlled or managed by the software. Without software, the physical body, your physical body is useless. Basically, without your functioning mind or brain, nothing is going to function. So that there are two categories of software, two big categories of software. The system software, such as your operating systems, and application software are the biggest category. That's where thousands, if not tens of thousands and millions of different types of software exist. There are a handful of the system software, such as Android, such as Windows, such as iOS, but there are millions and millions of different types of application software. So when you are in a class like Introduction to Programming, for example, you develop application software. You do not develop system software. System software, there are other smaller components of system software, but main focus here, and just remember, it's the much more complex and a larger system, such as an operating system. So programs that control and manage the basic operations of a computer are referred as system software. I indicated the operating system, OS, and it basically manages all the operations, such as how to connect to a physical device, how to load the data, how to run a program. All these are managed. Everything is managed by the operating system. There are additional system software, we call them utility programs. They perform specific tasks, such as a backup, such as protecting the data. And then you have certain tools, modify test software. Even some authors even put programming languages as system software as well. So you might hear these kind of programs which are called system software. And this is where most of us you specialize. You specialize in application software. These are the people mostly we use in our daily lives, such as I indicated some of them earlier, but word processors, PDFs, spreadsheets, such as Excel, database management system, directly or indirectly. Many of you don't use database management system directly because behind the scene, it is being managed automatically, but many other types of software, presentations and video games, and all these are different types of application software. Now, all data that is stored in computer is converted into sequence of zeros and ones. So let me spend a minute or so on the data. Now, data is not software. A lot of the students, they confuse the data as software. Data is basically incoming data. Data is such as 25. That is data. Now you bring 25 as an input to your software, to your program, and then you process it. So then you take 25, 23, 24, you add them all together, you can take an average. Now the program which is taking all the inputs and calculating the average, that is a computer program, but the data is 25, 24, and 23. So the data itself is the key component. That's why we use computers, because we are interested in results which can produce useful information for us to make better decisions. That's what the purpose of computers are. Computers basically make it much more efficient, and we can do a lot of readability much quicker. We can store it. Humans do not have the capacity to do that efficiently. Computers can do that 24 hours, 365 days. They can actually have the ability to do this consistently. And that's what we see, all the computers running around the world all the time. So the data is converted into ones and zeros. That's what it's highlighting in this slide. And we'll spend a little bit more time in this slide here. So computer's memory is divided into tiny storage, called them bytes. So bytes have 8 bits. All right, you can see an image down there. So they have 8 bits. Some bits can be turned on and off, as you can see. The first bit here, the first bit on the right-hand side, it's turned on. When it's on, the value will be 1. The second bit's value is 2, 4, 6, 8, 16, 32, 64. So this is how bits can be turned on and off. If the bit is turned on, the value will be added to it. If the bit is off, then of course it is not being used at that time. So each bit represents a number. Like I indicated, the first bit will represent 1, then 2, then 4, then 6, 8, 16, 32, 64, 128. I made a mistake earlier. The last one is 128. Not, I think I made a mistake here. So 1, 2, 4, 8, 16, 32, 64, and 128. So this is how bits are turned on and off. A byte is divided into 8 smaller storage, call them bits. Bits are tiny electrical components. So bits are tiny electrical components that can hold either a positive or negative charge. A positive charge is like a on button. So when you turn it on, it is like on position. And when the charge is negative, the switch is turned off. So that's how you store the data. Storing numbers, for example, the positive charge on the on position representing the digit 1. So as indicated here, digit 1. And you can see the value of digits are shown here because 2 to the power 0, anything power 0 becomes 1. Then 2, then 4, then 8, 16, 32, 64, and 128. 2 to the power 7 is 128. So this is how the powers are indicated here. And of course, when the bit is turned off, nothing will be used at that time. So this corresponds to the binary numbering system where all the numeric values are written as sequence of zeros and ones. Although this class is not, it doesn't go in too much detail, but you'll be taking separate classes where you'll be learning more about in fact, we do have one exercise, which I'll talk about it later on, where you will convert a decimal into binary and binary into decimal. Once you read the material in chapter number 1, you will learn how to do that. And it's not very hard because let's say I want to indicate let's say a value 7. So I can turn on the first bit because first bit is 1. I can turn on the second bit, that is 2. I can turn on the third bit, that is 4. So 4, 2, that's 6, and 1, 7. I can turn off all other bits to 0. If all of the bits are 0, the first, second, and third are turned on. That will basically indicate value 7. So this is how you can actually represent each one of these value. And in the next couple of slides, you will see some numbering system which we have created. These numbering system allow us to indicate more useful information. Now this slide here is much better because it tells us the value of each one of those bits. As you can see from the right hand side, the first bit is represents 1, then 2, 4, 8, 16, 32, 64, and 128. So if you have these certain bits on, the last one and these other bits are on, as you can see. So you can see the value in shown over here. So this will represent 157 if this is how the values are turned on, and it shows on the left hand side very similar kind of setup as well. So this example gives you pretty good idea how the bits can be turned on and off. You add up all the values which are turned on, and you exclude the values which are turned off, and then you can actually have a greater understanding how the number system. The question is that how do I convert these bits into characters such as ABC or such as a comma or a space bar or a plus symbol and all these things. So for that purpose, we have developed systems called ASCII system or Unicode system, which you'll see in the next slide or so. But here in this slide, it says the largest value that can be stored in a byte with the 8 bits, all bits are turned on, is 255. So if you turn on all of them, it will represent 65 in case of ASCII system. Now, if you have 2 bytes, which is indicated in the figure below, with the image below, they have 2 bytes next to each other. Because if you have just the first 1 byte each byte has 8 bits, the largest value will be 255. But if you have 2 bytes simultaneously next to each other, then the maximum, the largest value will be 36, I believe, not 35, 36. And I think they made a mistake here. It should be 65,536. So is it 35? Yeah, yeah, okay. So let me correct myself. Yes, the largest value will be 65,535. Plus, if you turn off all the bits to zero, that particular case will be another state. Then you'll have 65,536 different states. So here it is not showing you all the bits turned off because it is possible all the bits are turned off. That will be another state. Including that state, it will be 65,536. So this one is showing, just demonstrating what if all the bits are turned on, what will be indicated. But remember, there's another state when all the bits are turned off as well. All right, so one of the system called ASCII system. ASCII system allows us to indicate stands for American Standard Code for Information Interchange because this system has been developed, and you can simply go to Google and type ASCII. It will show you what the ASCII is going to look like. So for uppercase A is indicated as a fictitious number 65. So whenever you type uppercase A on your keyboard, so we have given a fictitious value of 65 in ASCII chart. So that indicates uppercase A, and this is how the computer processor understands it. And if you turn on the bit, the first one and the seventh one, because seventh one has a value of 64, so 64 plus 1 is 65. So this is how in the binary numbering system, or in a bit level, this is how uppercase represented. Now, lowercase a is actually greater because lowercase has a value of 97. So lowercase a in ASCII chart is much greater than uppercase a. All right, so then ASCII has a set of 128 numeric codes. And again, you can see they're turned on and off, which I showed you earlier. ASCII is limited because it only uses 1 byte. So Unicode actually has more flexibility because it has 2 bytes. So it is compatible with ASCII, as well as it also has an ability to represent many characters from many different languages because it can store 65,536 different characters, which we saw over here, 65,536. 35 plus 1 is when you have turned off everything else. So again, we are not going to spend too much time on this one because that's not the purpose here, just general understanding that what is the difference between ASCII chart versus Unicode chart. Advanced number storage, binary numbering system can be used to represent only integer numbers, negative numbers. We call it two complements. Two complements, when you have the first bit is 1, then it represents a negative sign. And the real numbers are encoded using floating points notation. Real numbers are basically something you can also have decimal places. The other types of data, digital data is data that is stored in a binary numbering system. Digital devices, such as all the devices you use these days, your computers and smartphones, they are digital devices. That's the digital data they store. The words we use or the speech we use as humans, or other kind of sounds you hear, birds and other types of sounds, they don't use digital sounds. They don't use digital data. I don't talk like binary numbering system. I don't talk like 1 and 0. The computers can only talk in ones and zeros. The humans, they use analog signals. The devices, smartphones and computers, they use digital signals. So we convert this analog signal from humans to digital signals. And that there's a built-in device called modem, modulator and demodulator, modulation, demodulation. That's why it's called modem. And that's how we convert them. Again, that's not the discussion of this class here, but this is how the humans can interact with machines, because humans, they use analog signals and machines, they use digital signals. So similarly, digital images composed of tiny dots of color known as pixels, picture elements, and digital sound is broken into smaller known as samples. So computer CPU can only understand instructions that are written in machine language. Machine language is only ones and zeros. We don't speak ones and zeros. We used to in 1930s and 40s because we did not have computer programming languages at that time. It was very cumbersome, very difficult. And that's what it's highlighting here. People find it very difficult to write the code in machine language. So they had to invent programming languages. Programming languages are not human languages, but they're pretty close. So such as Java and C++ and Python, these languages, they're easy to learn, and then you can communicate with the machine and you can write instructions. So CPU is the most important component in a computer, as we talked about it. I actually kind of disagree because CPU works like a brain, and your author in this textbook is says not a brain. So we'll follow whatever question you have in the exam. So if it says not a brain, just say not a brain. But actually, it works like a brain because that's the smartest component. That's where all the processing takes place. And CPU is an electronic device. It's a physical device that's designed to do specific tasks. And we saw that earlier as well. So CPU is designed to perform the following operations: read a piece of data from main memory, adding two numbers, subtracting one number from another number, multiplying two numbers. And of course, that's not all what we are doing, but behind the scene, just to keep it simple. So it can do a lot of different things, moving the data from one place to another place, determining what one values be equal or greater or less than another value, all sorts of processing. This is just some examples. These days we have not just one CPU, multiple CPUs, and especially you hear GPUs, graphical processing units, and you probably have heard a company called NVIDIA, and you probably have stock investment in NVIDIA. People who actually invested in NVIDIA 5, 10 years ago, they became very wealthy because they are the leaders, and especially after artificial intelligence, AI, they are have become leaders. So that's where basically the CPU or GPUs, they do all sorts of processing. So like we indicated, CPU only understands instructions written in a machine language. Machine languages are written only in ones and zeros. The entire set of instruction that CPU can execute is known as instruction set. Some of the companies very important for these kind of developments, the development of processors: Intel, AMD, Motorola, and I would actually put NVIDIA. NVIDIA is actually the leader, has emerged the leaders. And Intel was struggling, and in fact, there were some signs that they will go bankrupt or somebody will try to purchase them, and that was actually happening in last just a few months ago because some of the other leaders have taken over the market significantly. Now, here, this is called a machine cycle. Machine cycle, in fact, I would actually argue there are four steps to it. Your author says three steps. For sake of exam purposes, you'll stick to three steps, but there are four steps involved in machine cycle. Machine cycle includes fetch, decode, execute, and store. There are four steps, but here in this particular textbook, it only shows three steps. We'll stick to three steps: fetch, decode, execute. What it means is when the CPU receives an instruction or data, it fetches it, it decodes it. It decodes mean it tries to understand what needs to happen, and then it performs a specific task on it. So it fetches the instructions, it decodes it, makes some sense out of it, and follows some steps in order to process it. And this is called machine cycle. The fourth step actually is store. Once these three things have already have happened, then it stores it somewhere, either temporarily in memory, right there in the random access memory, or permanently in the hardware, such as hard drive or somewhere. All right, so from machine language to assembly language. So machine languages were very hard, and then gradually developed low-level language called assembly language, which is still being used. So computers, like we stated several times, they only understand machine language, but they are very hard to write, ones and zeros. So assembly language use some short words, mnemonics, that's what we call them. And there's a program called assembler. Assembler is basically a program which converts the assembly code into machine code. So assembler is needed to convert your assembly code into machine code. But even assembly was not good enough for us. So we developed other languages, which we'll see in a second. So here you can see move this variable and to this and add this to this and move this one this. And then assembler is a program which basically converts these instructions into ones and zeros or machine code. So like I stated, assembly language is pretty low level language. It has only limitations, although it is powerful, but and it is pretty close to machine language, but it is not good enough for people to write the code independently and different types of code. So then we start developing high-level languages. High-level languages, you probably have heard some of them. The first ever high-level language was Fortran. Fortran was the first ever one. I think it was developed in 1954. From now on, after that, we have hundreds and hundreds of high-level languages. I actually have taught maybe a dozen different high-level languages in the last 20, 40 years. And I currently I teach C++, Python. Last semester I was teaching Java as well. I have taught C Sharp, Visual Basic at Long Beach City College. I've taught many, 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 many different programming languages, and many new languages will emerge in the future as well, especially now AI is taking over. So maybe different types of languages, not necessarily high-level languages, maybe different types of languages which will emerge, which will become very seamless to humans and machines. And that's already we are noticing that's already happening. So high-level languages allow you to create powerful and complex program without knowing how the CPU works, because we learned how different instructions can be given in high-level language, and those instructions are converted into something meaningful to CPU, and CPU performs those tasks. So what these languages have, they have some keywords. The keywords, they have some operators such as greater, less than, plus, minus, all these, and they have some rules. Those rules are called syntax. So these keywords are reserved words. They have a special meaning in that particular high-level language. And each one of these languages, some words are common in Java, C++, C Sharp, and C, and some words are different in other languages, but they have special meaning to that language. And operators, like I indicated, plus, minus, multiply, greater, less than, equality operator, all these, they have a special meaning. And by learning how the grammar of that language or syntax of that language works, you can actually make statements. Statements are basically your sentences in that language, which your CPU understands. So this is how the languages emerge. Now, these languages, like C++, it has something called compiler. So compiler is a program which converts your C++ code into machine code. Remember, we talked about assembler. Assembler is a program which converts your assembly code into machine code. Similarly, compiler does the same thing. And some languages use the interpreters, and some languages use the compilers. So Java has a compiler, Python has a compiler. JavaScript is an example of interpreter, and where we use something one line at a time. On the other hand, the compilers, they take a large amount of code. We call it source code written in high-level language. Sometimes we simply call it code. And then it follows the rules of the syntax. If there are syntax errors, such as spelling mistake or some kind of punctuation or operators are not used correctly, then those need to be corrected. Then it converts into machine code. So that's what the purpose of the compiler is, a program that translates the high-level language into machine language. And it shows you right here. So this is written in high-level language. Compiler converts into this form, or this machine code is fed into CPU, and CPU can understand that one. On the other hand, the interpreter is a program that both translates and executes the instruction in a high-level language program. You can see that one line of code comes in, and then an interpreter actually converts into machine code, and it fits fed into the CPU. And the last slide here is a program generally fit into two categories, system software and application software. We spend most of the time discussing the application software. That's what we'll be spending most of the time in our class here. So just wanted to spend maybe 35, 40 minutes or so. So we are done with this chapter. So let me pause this one here, and then we will continue with chapter number 2. Thank you very much.